You going right into the next lecture?
Yep.
Can I talk with you?
Oh, of course, yeah.
Um,
mean, What's the cut for Finite?
Thursday, November 22nd. So it's gonna be the last Thursday of 22nd.
Okay,
Yeah. Mhm.
Who's from bus?
I have no idea. I assume so. You can erase it.
I'm also going to catch up in optimizing.
Okay, sounds good.
I was studying for like these combustion class.
Oh, I see. Oh, do you have a midterm recently?
Midterm tomorrow.
Oh, dang. Oh,
So
pretty
now-
early, pretty early.
Yeah.
That's good.
Yeah, second midterm.
Okay.
I was just trying to finish up during optimization.
Oh, okay. I see. I see.
Now I'll catch up.
Okay, sounds good.
Before you got to the battery, I dropped it off at 21. Everyone thought Costco opened it and got the battery. Sorry, thank you. Thank you for the offer. I have like a whole day today. No, I didn't drop it in the bottom. Yeah, so it's wrapped around the hole. Yeah, yeah, so it's wrapped around the hole. Yeah, oh, okay. If it is, I'm gonna go vote.
Hey, what's up?
Nothing, just, we're gonna do roller pin fit. Oh, so we're doing a review of
A little bit, yeah. Well, we're gonna see how it factors into
the fixed ones, okay.
yeah, how the rest of the meeting go.
It went good, everyone seemed interested,
That's
no one was falling asleep.
That's good.
Then
Good start.
Justin was like, okay, well, now that the professional is gone, I have a few videos I wanna show you, and it's a video of me crawling through the vent of a UCI, and I'm like, no, all my professional credibility is gone.
There's, I think it's like it's a or an informal requirement that there's some video of every Tau leader member, like either doing something silly with the vent or polishing. Like there's a video of me that may or may not be me. It's polishing the vent at UCLA.
Nice. I may or may not look for it.
Yeah.
No, yeah, but if you were able to stay a little bit longer, we reached the end and then I answered questions and then I'm also gonna give you we're probably gonna send another email to everyone.
Okay,
Oh, well, I have everyone's email now, so I could probably send it out.
okay, yeah,
Because I requested at the end that they draw the vent. Since
yes.
Our vent's mobile, so I can't really do a vent polish.
We can, I mean, you can bring it out and polish it, but,
Yeah, but it's also, we have to put it like on bricks.
oh, yeah, I guess.
So I'm just, and either way, it's not tarnished. It's been in a closet.
Yeah, it's dusty.
Yeah, but like, that's just a wet rag.
Yeah.
It doesn't need, it's not a
Well,
polishing.
everyone can take one turn, just doing one
One
swipe.
line.
Yeah,
But yeah, so now instead, I'm gonna have them draw the vent.
okay,
Or 3D print it, whatever they want.
sure, that sounds good.
Just to see artisticness. But
Yeah.
everyone seemed very involved. Everyone shook my hand. No one seemed. It was very formal at the start.
That's good, that's good. Was there a lot of people on Zoom too?
There was one person on,
Okay,
and then Sam. Sam
okay,
was on.
yeah, I heard, I should have said that.
It's fine. No, yeah, it was it went well.
It's good,
And then a lot of people were interested. All the graduates were really interested.
yeah, I've gotten questions from.
Yeah, same here I have some few questions by some students who were like, oh, hey, I can't make it. And then they didn't show up to the Zoom.
Okay,
They asked like, hey, how can I join? I'm like, oh, there's a Zoom meeting. Like, kids, you just can't make it.
Yeah.
I think you were there at the start where I'm like, I understand if you can't. Because 3 of our members have kids, 2 of them have full-time jobs. I understand. Life gets busy.
yeah,
And then they had a lot of them, there was a question of like, so what do you do at initiation? And I'm like, I looked at Sam and Sam was like, you basically get an input dump on all that's happening. I'm like, yeah, I didn't know what to say. I was like.
That's why Sam's there. That's good, I'm glad.
But overall, it went really well.
That's good. And the bowling next week.
3 to 5.
Okay,
You still have class, maybe you can make it for 3.
yeah. Yeah, no, I'll come, I'll do a few celebrity shots.
You missed it at the end, just because I was trying to break the professional tension also. I was
Yeah.
like, hey guys. I'll be honest, I'm very competitive.
Yeah.
But I'm also very bad at bowling. So we'll see how this goes.
It's good, that's good,
And that broke the ice, everyone laughed.
that's good.
Everyone was a little bit awkward. I'm like, congrats on all of you for achieving like the 1/5, 1/8,
Yeah.
or reaching your graduate, finishing your first like year with still good academic standing. They give up applause, and then everyone was like,
Oh, yeah, I was there for that.
yeah, the awkward claps.
Yeah,
I was like, yeah, you're so proud of applause.
yeah. It's good, it's good. I'm glad there was a lot of kids.
Overall, everyone on that sign up list, I didn't see anything. They were all like attentive.
Okay,
All of them, like, when they asked questions, they all nodding.
okay,
Very respectable.
Good, good.
I think the video of me crawling through the bed broke the end because
That's good. I think that's important. You want, it's professional, but you also have fun. So I think that's important. I mean, like you said, Tau Beta Pi is all about networking, and you want to network with for people. So good. No, you guys did really good.
I'm glad Justin was there to like break the ice. I dealt with all the professional matters and he was like breaking the ice. It just happened to be, it was a video.
You guys make a good team.
Couldn't do it without him, but last.
All right, it's 5:30. Let's go ahead and get started. All right, good afternoon, everyone. Good evening. How's everyone doing?
Good.
It's election day. Hopefully everyone voted. Yeah, I think polls are open until 8 o'clock. So I think you can well, you can leave now and go vote, or you can go after class and vote.
I'm gonna go do my.
Good. Yes, do that. Yeah, so if you haven't voted yet and you are close to a polling location, go vote. Remember, this lecture is recorded, so you can go and do that. Make sure you do that because vote. The democracy only works if everyone votes, and so if it's only just old people voting, then that's not democracy. That's just old people deciding everything. So yeah, vote. Definitely vote if you haven't had the chance yet. All right, but for today, back to finite elements. We're going to continue on. So we are starting a new chapter today. So we are done talking about trusses, and so we spent a bit more time on trusses than I originally hoped. So this week is going to be all about beams. So we're going to introduce a new element type, and so we'll see how beams kind of differ from trusses and springs. We'll do some examples for that, and then we'll kind of close. I'm hoping that by the end of this week, we'll close up this chapter on direct stiffness method, so we can get back to ANSYS. All right, so last Thursday, your midterm projects were submitted, so I'm working my way through grading them. I think I'm about maybe 2/3 of the way done, so I'm definitely on track to finish all of them by Thursday. So before class on Thursday, you'll know your grade. And on the rubrics for everyone's projects, I'm leaving comments too. Just to kind of give you guys feedback. Not all of them, just because so a lot of you guys did really well. So there weren't for some of you there weren't too many comments other than just saying good job. But make sure you kind of read the comments that I need. Okay. All right. Another announcement. Remember, homework set 1 is out there. Even though I say problem set 1, it's the only problem set. So it's the only time in this class where you'll be doing an assignment outside of ANSYS. So the problem set, you can think of it as kind of your chance to practice these problems before the midterm. And I believe it is due, actually, let me double check. I believe it's due the Sunday before that week. Well, I can't log in my phone right now, but actually let me check. I have Canvas up. Let me check on Canvas. assignments. Problem set 1, due on Monday, November 18th. Okay. And I want to warn you guys, it is a long homework assignment, and so it does take a while. So, I know everyone just got done finishing the midterm project, but we need to kind of get this this direct stiffness done before Thanksgiving. And so, we have the midterm right before Thanksgiving, so I want to make sure you guys get enough practice with direct stiffness problems. So the problem set is due Monday, November 18th, but don't wait until next week to start it. And so at this point, you guys should be able to do, we've gone over 1D problems, we've gone over 2D trusses, so you should be able to do maybe 70% of the homework. So, definitely get started on that. Don't wait until next week. It's gonna take you a while. The problems themselves are long, and it's very easy to get fatigued with these problems. So it's not the type of homework assignment you can just pound out in like 4 hours straight. You definitely have to do a problem. You have to kind of take a break just because you're going to get tired of seeing matrices and numbers and cosines and sines, and then kind of come back from there. So definitely start it soon, just so that you can have enough time to finish everything. Okay. All right. Any questions I can answer before we get started for today? Yeah. Yeah. So I'm going to post. I'll post a solution the day after the homework is due. So you'll have that to study for the midterm before. Yeah.
Midterm about the 21st.
22nd, which is the Thursday. Is the 21st a Thursday or the 22nd? Or 21st? Okay, so Thursday the 21st is that's when the midterm is. Okay. All right. Any other questions on this before we get started for today? Okay. All right. So let's go ahead and get started. All right. So last time we met up, we were finishing up our lecture on truss equations. So we spent quite a bit of time with trusses, talking about 1D trusses, 2D truss problems. So now we're going to move on to a different element type. Okay. Okay. So different types of elements is not something that's unique to direct stiffness, right? So finite elements is still with all different types of elements. Even in ANSYS, we've gone over quite a few. So, we have tetrahedral elements, hexahedral elements, quadratic linear elements. So in direct stiffness, there's a lot of these different types. And, one of the really kind of interesting things about finite elements is that you can combine all these different element types together, and you can still kind of get a cohesive solution. Okay. And so the types of elements that we're going to go over today are called beam elements. Okay. So we've seen beam elements before. So if you think back to ANSYS activity 4, a big part of that activity was going over beam elements. Okay. And what did I mention, and what did we discuss back then, right? When you compare a beam element compared to a kind of a traditional solid element, one of the unique qualities was that we said beam elements account for the rotation of the element itself. So in addition, okay, so every solid element type will compute deformations. And so we saw that in our springs and trusses as well. Okay. What's unique about beam is that in addition to deformation, we're also going to solve for the element's rotations. Okay. All right, so let's kind of see what that looks like. And so, we have kind of our standard kind of slender element that looks like this. Okay. And so the left side of the element, we're going to call that node 1. And the right side of the element, we're going to call that node 2. Okay. All right. So far, in our truss elements, we've only considered axial deformation. So that's deformation that's parallel to the element itself. Okay. For beam elements, we're going to consider all other modes of deformation. And so what does that look like? And so, another way that a slender element can deform is that it can deform perpendicular to the element itself. Okay. We have a D1Y, D2Y. Okay. So D1Y and D2Y here, these represent what's called transverse deformation. Okay. In other words, that's deformation that's perpendicular to the element itself. Okay. So that's nothing too new, and it's just kind of adding another dimension to our deformation. But D1Y, D2Y, those are deformations at its core. Okay. So what's unique about beams is that in addition to the transverse deformation, we can also compute the orientation or the slant of the elements at those nodes. Okay. And so we denote those by angles. So theta 1, theta 2. So theta 1, theta 2 represent the element's orientation or tilt at nodes 1 and node 2. Okay. So the beam elements that we're going to consider, from here on out are going to be, are going to have transverse deformation. So that's new. And it's also going to have rotation as well. Okay. So these four quantities, these are now going to be our degrees of freedom for our beam elements. Okay. All right. So when we consider the transverse deformation, we consider the rotation, and we put that together with our truss deformations, which are the axial deformations. We basically covered all of our bases for 2D deformation of elements. Okay. And so just to kind of paint the picture here, truss elements and spring elements only have axial deformation. Okay. They have D1X and D2X. Okay. And I guess if you want to be specific, these are all deformations that are local to the element itself. Okay, so everything here should have. Okay, so that's the idea with beams. And so with beam elements, we're going to consider transverse deformation and rotation. And so we're going to ignore axial deformation for now. Okay, we're going to bring those back. And so eventually, we're going to be able to do problems with, beams and trusses and springs all together. And so, those things are not going to go away. But for now, we're just going to focus on the transverse deformation and the rotations. Okay. All right. Any questions on this? Okay, good. All right. So next thing we need in order to do problems is we need the element stiffness matrix for a beam. So in the notes, you'll see that there is a derivation based on beam theory. I go through the Euler-Bernoulli beam equation, and I use that to derive the element stiffness matrix. We are a little bit behind, so I'm going to go ahead and skip that derivation, and I'm just going to give you the formula for the element stiffness matrix straight up. Okay. Okay. So this is derived through the Euler-Bernoulli details in the notes. But the element stiffness matrix is the following. All right, so first thing to note here is we have our constant factor out in front. We have E. E is a familiar player here. E is the Young's modulus of our element. I is something new, so I is the moment of inertia of the cross-section of our element. And we have L, which is the length of the element, which again is a familiar commodity. Okay. All right, so our element stiffness matrix for a beam is 4 by 4, because for every beam element, we have 4 degrees of freedom. We have the transverse deformation at each node and the rotation at each node as well. So that's going to be four entries. Okay. And so our element stiffness matrix here is 12, 6L, minus 12, 6L. Okay. That's the first row of the matrix. And once again, I'm going to use the same trick that we used for the 2D truss element stiffness matrix. And just know that this is symmetric. And so whenever you write a row, you can write it into a column. Okay. I'm going to leave the column blank just to kind of, save myself a bit of time, but just remember that you can write it into the column there as well. Okay. All right, second row. We're going to start with the diagonal entry. So we have 4L squared minus 6L and then 2L squared. Okay. Third row, we have a 12 and the diagonal entry, and then a minus 6L, and then 4L squared. Okay. Then we're going to multiply this by the degrees of freedom of the node itself. Okay. So here's where it gets a bit interesting, because we're actually kind of mixing different quantities with different units within the same matrix. Okay. Okay. So first row, that's going to be a transverse deformation row, so that's D1Y. Second row, it's going to be a rotational deformation, so that's theta 1. Then third row is going to be D2Y, and then fourth row is theta 2. Okay. So that's the matrix itself. And then on the right-hand side, we have the corresponding nodal forces, or nodal loads. Okay? We have F1Y, M1, F2Y, and M2. Okay, so that is our element stiffness matrix there. Let me label a few newcomers here. Okay. I'll just label everything here. So E here is the Young's modulus of the element. Okay. I here is the moment of inertia. Of the cross section. Okay. L there is the length of the element. Okay. And then the other newcomer here is on the right-hand side. So on the right-hand side, for that forcing vector, we typically only have nodal forces. But for our rotations, we instead have nodal moments or nodal torques. Okay. M1 and M2, these are the nodal forces, or nodal moments, excuse me. So those are the moments that are acting on the nodes, right? So sometimes you'll hear me call them torques. Torques and moment, in this context are kind of interchangeable. All right. Any questions on the element stiffness matrix for a beam? Okay. All right. So that's the main part of this lecture here. And so we're going to be doing some examples soon. So for the examples, they're going to follow the exact same process that we've done before. The only thing is that for beams we're going to use this element stiffness matrix instead of the other one. But we're still going to follow the same process of element stiffness matrix, assembly, boundary conditions, and solve. Okay? The only thing that changes here is the element stiffness matrix. Okay? But before we jump into an example, I do want to revisit the idea of the supports. Okay. Or in other words, we're looking at the constraint type boundary conditions. Okay. Because now we have a bit more to think about because we have so many different dimensions of deformation. Okay. So if you think back to the way that we usually apply our boundary conditions or our constraint type boundary conditions, remember the way we apply them is we cancel out entire rows of our global stiffness system. Okay. Okay. And so the rows that we end up replacing for our global system depend on the degrees of freedom that are constrained. Okay. And so if you think back to the last example that we did, last Thursday, we introduced this concept of a roller support. And so with the roller support, we only cancel out one dimension of the deformation. Okay. So when we kind of when we started doing 2D problems, we kind of introduced this concept that each node can have multiple degrees of freedom. You can have an X deformation and a Y deformation. Okay. If you're fully constraining that node, so back then a full constraint would just be a pin support. Okay, a pin support would cancel out both the X and Y deformations at that node. Right. But if we had a roller support, that means we'd only cancel out one component of the deformation, and we'd leave the other one free to do what it wants. Okay. So now that we're introducing this idea of a rotational degree of freedom, we need to know how that degree of freedom is constrained relative to the constraints that we have. Okay. All right. So for our beam equations here, we actually have three types of constraints. Okay. And so I'm going to go from most constraining to least constraining. All right, so the first one that we have is a fixed support. So a fixed support is the most constraining thing that you can have, right? Visually, the way that we kind of draw this is that we kind of draw it as if the beam is kind of stuck or welded to a wall. So you can see here the beam is kind of stuck. It's almost just like it's kind of jutting out of the wall itself. Okay, so this is the most constraining. And so all three dimensions or all three types of deformation are going to be constrained in this with this support. Okay, so you have d1x is equal to 0, d1y is equal to 0, and theta1 is equal to 0 here. Okay. Where node 1 would be the node that's attached to the wall. So fixed support, all degrees of freedom constraint. Okay. Second type of constraint that we have is a pin constraint or pin support. Okay. So pin support is basically a support that looks like this. Okay. So it looks like the beam itself is kind of pinned to the ground. Okay. And so for a pin support will constrain all of the dimensions of deformation. So d1x, d1y are equal to 0. But the thing that separates a pin support from a fixed support is that a pin support is allowed to rotate, okay? And so the theta dimension here is actually going to be free. So a pin support, the way to kind of summarize it is that it does not constrain rotation. Okay. And then finally, we have the roller support. The roller support visually looks something like this. We have our beam. So it's on a support, but that support has wheels, okay? So the roller support here is only going to constrain one dimension of deformation, and that's going to be the deformation that's perpendicular to the roller. And so in this case, the y direction is the one that's constrained. And so d1x here is actually going to be free. d1y is going to be 0. And theta1 here is going to be free. Okay. Okay. So when you're doing these beam problems, definitely pay close attention to the types of supports that you have, because that's going to change how you apply the boundary conditions to your global meters. All right, any questions on this before we jump into an example? Okay, all right, so let's go ahead and do an example. Pretty straightforward one, but just to kind of show you how this all kind of works out. Okay. So let's consider the following structure that has two beam elements. Okay. All right, so first thing we have here is we have a wall. So that we have one node here that's going to be fixed to that wall. So you have node 1 here. Okay. So this first beam here, that's going to be beam A. And then beam A is going to be connected to another beam here. So that's going to be beam B. Okay. So we have 3 nodes here. So you have node 1 that's fixed to the wall. Node 2 that's going to be right in between elements A and B. And then node 3 here that's going to be at the end. Okay. All right, so we're going to assume that each of the beams are identical. So they each have the same length. And they're going to have the same Young's modulus and same moment of inertia as well. Okay. So E, I, same for both elements. All right. Let's include some loads. And so all of our loads here are going to be applied at node 2. And so first load that we have here is we have a downward force that is has magnitude P. Okay. And we're going to include another load at that node as well. Okay. And so we have a moment or a torque M that's being applied at node 2 as well. Okay. Right, so we can say force load P and moment load M, both applied at node 2. Okay. Oh, forgot one extra support here. Okay. So the last thing to add here is that we actually have another support. So we have a pin support at node 3. Okay. All right, so that's our problem. And so what we want to do here, so I'm not giving you any numbers here, so we're just going to do this problem completely in symbols, is, let's write out the global stiffness matrix along with the boundary conditions applied. Okay. All right, so let's compute. Compute the global stiffness matrix with boundary conditions applied. All right. Any questions on just how this problem is set up here? Okay. All right. So let's go ahead and run through the problem. Okay. So we have ourselves kind of a very classical kind of direct stiffness problem, except with beams, right? So that's kind of the only new wrinkle here is that we have new beam elements. But we're going to solve this in the exact same way that we did before. So we're going to first start out with the element stiffness matrices of each element. Okay. All right, so this part here is not going to be too exciting just because we don't have numbers to plug in, but let's write out the element stiffness matrices for elements A and B, okay? Remember, one important part of the element stiffness matrices is that you have to indicate which nodes that element is connected to. Okay. Okay, so let's start with element A. Okay, so element A, we write out its element stiffness matrix EI over L cubed. And then we have our 4x4 system here. So we have 12, 6L minus 12, 6L. Okay. I'm going to write out the full element stiffness matrix here. So I'm going to write out the columns from the rows here. So this is 6L minus 12, 6L, 4L squared minus 6L, 2L squared. Okay. Minus 6L, 2L squared. Okay. So I'm doing what we usually do is we kind of build up these matrices kind of row by row, right? So we start with first row, we write into the first column. Second row, we write into the second column. Okay. Okay, and we multiply that by our degrees of freedom for the nodes that we are connected to. Okay. So element A here is connected to nodes 1 and 2. So that's D1Y theta 1, D2Y theta 2. Okay. All right, and then element B is going to be the exact same. The only difference is that element B is connected to nodes 2 and 3. Okay, so it's EI over L cubed multiplied by 12, 6L minus 12, 6L, 6L minus 12, 6L. Okay. So the matrix itself is exactly the same. Okay. And that's because the both beings here are exactly the same. Okay. The only difference here is that element B is connected to nodes 2 and 3. So we have D2Y, theta 2, D3Y, theta 3. Okay. And so of course, if we had numbers for this, we'd plug in the numbers here, but this is just kind of a quick example to start with. Any questions on how we got these matrices here? Okay, good. All right, so the next step is assembly. Okay. So we're going to assemble our global stiffness matrix from here. Okay. So remember, our global stiffness matrix is the matrix that's going to govern the behavior of our system as a whole. And so it has to include all of the degrees of freedom for all of the nodes in our system. Okay. So we have 3 nodes in total, and each of those 3 nodes are going to have 2 degrees of freedom. They're going to have a transverse deformation and a rotation. That means in total, our global stiffness matrix here should have 6 rows and 6 columns. So it's a 6x6 matrix. Okay. Okay, so let me leave myself enough room to write everything here. Okay. And so the 6 rows of our matrix are going to correspond to each of the degrees of freedom. So we have D1Y, theta 1, D2Y, theta 2, D3Y, theta 3. Okay. This is all equal to the nodal forces. So we have F1Y, M1, F2Y, M2, F3Y, M3. Okay. And let me write out the columns as well. So we have D1y, theta 1, D2y, theta 2, D3y, theta 3. Okay. So the columns there just match the rows. Okay. So just like we usually do at this point, we're going to take our element stiffness matrices and insert them into the global stiffness matrix, depending on which nodes that they are aligned with. Okay. Okay, so let's start with element A. We know element A is connected to nodes 1 and 2. And so that's going to be this section of the matrix right here. Okay. And then element B. Element B is just nodes 2 and 3. Okay. So nodes 2 and 3 are going to be this section right here. All right, so let's go ahead and fill in each of the element stiffness matrices, remembering that whenever you have an element stiffness matrix that overlaps with another one, you're just going to add those entries together. Okay. Okay, so let's start with element A. So element A here, we have 12, 6L, minus 12, 6L, okay, 6L, minus 12, 6L. Okay. We have 4L squared, 6L, 2L squared. Next, we have the overlap region. So I'm just going to leave some space there in order for us to add the entries from element B. Okay. We have 12 minus 6L, minus 6L, and then 4L squared. Okay. And then we have the same thing for element B. So element B here, we're going to add the plus 12 plus 6L minus 12, 6L. Okay. We have a positive 6L minus 12, 6L. Okay. Second row, we have a 4L squared. We're going to add that there. Minus 6L, 2L squared. And then 12 minus 6L, minus 6L, 4L squared. Okay. And everywhere that we don't have any overlap or we don't have any element stiffness matrix, we're just going to put zeros there. Okay. All right. This is why I recommend that you guys start the homework early, because you get tired of writing matrices very, very quickly. Yeah. So if you stare at these long enough, then you kind of start to go crazy. So you have to give your mind a break. All right, so I'm going to go ahead and perform the addition for the entries that are overlapped. Okay, so everything here in this overlap region, I'm just going to go ahead and erase and just write out the sum. Okay. Okay, so in this region here, we have a 24. The two off diagonal entries are going to be 0, and then 8L squared. Okay. All right. All right, so the next step in our process here is we need to apply our boundary conditions, and so that means applying our fixed supports, our pin supports, and our loads. Okay. So the first boundary condition that we have is a fixed support. We have fixed support on node 1. Okay. So remember what a fixed support does. So a fixed support is going to knock out, or it's going to constrain both the deformation and the rotation as well. Okay. So that means we're going to replace both the first row and the second row of this matrix. Okay. So the first row here, like that. Second row, just like that. Okay. All right, so let's do what we usually do. So let's replace all the non-zero entries with 0 in the left-hand side matrix. Make sure we put a 1 on the diagonal. So we have a 1 in the first entry there, and then zeros on everywhere else. And then for the second row, we have 0, 1, 0, 0, 0, 0. And then in the right-hand side vector here, we're going to replace f1y with 0, and then m1 with 0 as well. Okay. All right, so that's our first boundary condition. So that knocked out 2 rows in our matrix. Next thing we need to apply is our second constraint. So our second constraint here is a pin support on node 3. So pin support, remember, a pin support does not constrain our rotation. And so we're going to leave the last row of this matrix alone, actually. So the only row that this actually knocks out is the 5th row in the matrix. Okay. So the pin support is only going to put constraints on D3Y. Okay. Theta 3 is going to be left free. So we leave theta 3, the theta 3 row alone. Okay. Okay, but for this row, we're going to do exactly the same thing we did with the first 2 rows. So we're going to replace all of the entries here. Okay. Okay, so we replace everything in that row with zeros except for the diagonal entry. So the diagonal entry here is going to be the 5th column because this is the 5th row. Okay. And then on the right-hand side vector, we include a 0. Okay, good. All right, so the last thing that we need to apply here are our 2 modes. Okay. All right, so first thing that we have is we have a force load of P that's being applied on node 2. Okay. Now we have to be careful of the sign here. And so if you look back at the figure for this problem, we see that the load P is being pointed in the downwards direction. Okay. So that means we replace F2Y here with a minus P. Okay. And then for the moment load, the other thing that we have is we have a moment load also applied on node 2. And so a moment load is going to replace the entry in the theta 2 row. Okay. And so we're going to place M2 here with F. Okay, so the last thing that we have to set here is that on node 3, we don't, for at least for theta 3, we don't have any load and we don't have any constraints. And so we're just gonna replace M3 there with a 0. Okay. All right, and so that's our matrix. And so our matrix here, we've gone ahead and we've assembled all the element stiffness matrices. We applied our boundary conditions, and we're ready to solve. And so theoretically, if we were to have numbers for this problem, we can plug them in, and then we can plug these matrices into MATLAB and get our solution for D1, theta 1, D2, theta 2, D3, and theta. Okay. All right, any questions on this example here, how we applied the boundary conditions, how we assembled any of that? Okay, good. All right, and so that's beams, right? And so, this is the exact same process that we've done before. If anything, maybe that last example was a little bit boring. So, beams, the only thing you have to really be aware of is, first of all, the deformation modes for the beams are completely different. So they're going to be transverse and rotational as opposed to axial. And then you also need to be aware of the different types of support that we have as well. Okay. All right, so let's jump into another example. This one's going to be a little bit more interesting because we're going to combine our beams together with a spring. Okay. Okay. So in this example, we're going to do a beam that's supported by a spring on one side. Okay. So the figure for this one looks something like this. So once again, we have a fixed support at the wall. We're gonna have two beams here. So we have, one beam that's kind of split into two. Okay. We have element A, element B. We have node 1 that's at the wall. Node 2 that's in between the two elements. And node 3 that's going to be at the end. Okay. So it looks very similar to the last example that we did, but instead of a pin support at the end, let's say that the end of that beam there is actually supported by a spring instead. Okay. Okay, so at the end there, we have a spring that's attached. The spring is perpendicular to the beams. That's going to be really important when we form our element stiffness matrices. Okay. And that beam is fixed to the ground at the bottom at node 4. Okay. All right. Let's talk loads. And so we have a load here that's applied on node 3. And so let's say that we have a load P that has a magnitude of 50 kilonewtons being applied on node 3. Okay. And unlike the last problem, we're actually going to do some numbers here. So we're actually going to plug in and see how that all works out. Okay. All right. Let's start with the Young's modulus. So the Young's modulus for both beams are going to be the same. And so it's going to be 210 gigapascal. Okay. We have the moment of inertia. Moment of inertia is 2 times 10 to the minus 4 meters to the fourth. Okay. And then we have K. So this K is for the spring. Okay, so this is the spring constant for the spring. This is 200 kilonewtons per. Okay. Oh, we need the lengths. And the lengths for each of the beams is 3 meters. Okay. So it's a fairly long structure. So the entire structure there is 6 meters long. So that's pretty massive. Okay. All right, so what we want to compute. Let's compute the nodal deformations for each node in this structure. Okay. All right, any questions on the setup of the problem? Okay, all right, so, this is a slightly more interesting problem. So, we have numbers here, but also we have a spring, right? And so, we kind of just got done talking about how springs and beams have totally different deformation modes. And so, the question now is, how are we going to combine the element stiffness matrix of the spring together with those beams, right? So you'll see in a second, the key here is to note that the spring here is actually perpendicular to the beams itself. Okay. All right, but let's start this problem like we usually do. So let's start by writing the element stiffness matrices for each element. Okay. So actually, we're going to plug in numbers at the end. But just for the sake of simplicity, I'm going to go ahead and do this for symbols just for now. Okay. I would like to finish this example before we end it, but we'll see. Okay. So element A and element B are both beams, and in fact, they have identical properties once again. So I'm going to go ahead and just write out their element stiffness matrices very quickly. So element A, we have EI over L cubed multiplied by 12, 6L minus 12, 6L, 6L minus 12, 6L, 4L squared minus 6L, 2L squared. Okay. Element A is connected to nodes 1 and 2, and so our degrees of freedom here are going to be D1y, theta 1, D2y, theta 2. Okay. Element B is going to be exactly the same. The only difference is that element B is connected to nodes 2 and 3. So let's go ahead and write that down really quickly. We have the exact same element stiffness matrix as element A. The only difference there is that, we are connected to nodes 2 and 3. So D2y theta 2, D3y theta 3. Okay. Okay. That was a lot of writing, so I'll give everyone just a minute to catch up. Okay. Okay. So those are element stiffness matrices for the two beams. We do have one additional element here. I guess I didn't officially give it a name, but our spring here is element C. Okay. So element C is a spring. Technically, it's a two-dimensional spring. And so what we can say here is that, we can say that this is a 2D spring. Okay. And so for any 2D element that we've discussed before, whether that be trusses or spring, you have to define its angle. Okay. And so just like we usually do, we're going to go back to the element here. We can see that the lower numbered node is node 3. So what I'm going to do is I'm going to draw an x-axis that kind of originates from that. Okay. And I'm going to see how much we need to rotate in order to get the spring into the orientation that it's in. Okay. And so if we rotate counterclockwise, we can see that we rotate by an amount of 270 degrees, okay? And so theta here is 270 degrees, or if you use -90, that works too, okay? And so if we take sine and cosine, so cosine of 270 is going to be 0, sine of 270 is going to be -1, okay? So let's go ahead and plug in to solve for the element stiffness matrix here, okay? Okay, so for the element stiffness matrix for the spring, we have our spring constant K that's out in front, okay? Okay, so I'm going to go through this really quickly just because I know the cosine terms are 0, so everything with the cosine is just going to be 0. So that means the entire first row, we're just going to have 4 zeros in a row, so 0, 0, 0, 0. Okay. Second row is going to be 0, 1, 0, -1. Okay. And then this is going to be multiplied by the, first of all, it's nodes 3 and 4, but it's the transverse and axial deformations for nodes 3 and 4. Okay. So you have D3x, D3y, D4x, D4y. Okay. So at this point, we have our element stiffness matrices, and we should be ready to plug them into our matrix here. Okay. But before we do that, I'm going to make our lives a little bit easy. Okay. All right. So let's look at this element stiffness matrix here. Okay? So we can see here we have a column of all zeros here and rows of all zeros. So we have rows and columns of all zeros, and in fact, they correspond to the x deformations, D3x and D4x. Okay. And so what do we know happens when you have a row and column of all zeros? When you have a row and column of all zeros, that means there's no way for this structure, or at least for this element stiffness matrix, to interact with that degree of freedom, right? Because it's all just going to be zeros. Okay. And so, I want you to look at the directions for those deformations, right? So they're x direction deformations. If you look at all the other element stiffness matrices, in fact, actually the only one we have to look at is element B, because element B is the only other element that touches node 3, right? If we look at the degrees of freedom that we have available to us in element B, we have D3y and theta 3. Okay. What's missing from here? Right? We don't have any D3x in that matrix, right? And so even from the beam elements, there's no way for us to interact, or there's no way for us to affect any of the x deformations. So there's no way for us to affect D3x or D4x. Okay. And so since these degrees of freedom don't show up in any of the other element stiffness matrices, then, there's no way for us to affect their values at all, okay? And so if that's the case, if there's no way for us to affect those entries, let's go ahead and eliminate those from our system right off the bat, just so we don't have to worry about writing them out in our assembly. Okay. And so if we eliminate these rows of zeros, we eliminate these columns, okay? Our element stiffness matrix for the spring actually becomes a lot simpler, okay? And so for the spring, we end up with 1 minus 1 minus 1, 1, okay? Multiplied by k, then we have d3y, d4y. All right, so that saves us a lot of work. So that saves us from writing 2 whole rows and 2 whole columns in our global system, which, when our global systems are starting to get very large in terms of the number of rows and columns, this saves us a lot of work, okay? So before you kind of start jumping into assembly for these systems, try to take a moment to pause and see if you can simplify the system at all. Sometimes it can save you a lot of work. Okay. And so with that out of the way, let's go ahead and jump to assembly. Okay. So we're going to assemble our global stiffness matrix here. So let's count the number of degrees of freedom that we have. Okay. So we have 3 nodes that are connected to beams. Okay. So those are going to have 2 degrees of freedom associated with those nodes. So that's a dy and a theta. Okay, so that's already 6 rows and 6 columns that we have to account for. And then we also have 1 node here that's simply connected to a spring. Okay. So I know it's attached to the ground, so it's going to be zeroed out anyway. But just for completeness, let's go ahead and include it in our matrix. Okay. And so that node there, the one that's only connected to the spring, is only going to have a translational degree of freedom. So it's only going to have its actual deformation dy. Okay. So in total, the amount of rows and columns that our matrix is going to have is 7. Okay. So 7 rows, 7 columns. Okay. So let's go ahead and draw the matrix here. Okay. So let me write out the columns first. So our columns, we have d1y, theta 1, d2y, theta 2, d3y, theta 3, and then d4y. Okay. We have no theta 4 because, node 4 is not connected to a beam, so it doesn't have any rotational degrees of freedom. Okay. Okay, and then for the rows in the matrix, we have the exact same rows. You have d1y, theta 1, d2y, theta 2, d3y, theta 3, d4y. Okay, and this is equal to, we have f1y, m1, f2y, m2, f3y, m3, and f4y. Okay. So I think we'll have time for the assembly, but we won't have we'll save the boundary conditions for next time. Okay. So first thing we're going to assemble here are the beams. Okay. So the beam should be pretty straightforward. They're connected straight to each other. Okay. And so just like we did in the previous example, let's go ahead and put our constant out in front. Okay. So our constant for the beams is EI over L cubed. And let's start filling in. Okay. So first we have element A. Element A is connected to nodes 1 and 2. Okay. So let me go ahead and box out that area of the matrix there. Okay. Let me go ahead and fill in those entries there as well. We have 12, 6L, minus 12, 6L, 6L, minus 12, 6L, okay. 4L squared, 6L, 2L squared. Okay. And then we have this overlap region, so that's going to be 12, minus 6L, minus 6L, and a 4L squared. Okay. Okay, next we have element B. Element B is also a beam, and is connected to nodes 2 and 3. Okay. So that's going to be this section right here. Okay. Let me go ahead and write in these entries here. So we have a plus 12, plus 6L, minus 12, 6L, okay, plus 6L, minus 12, 6L, plus 4L squared, 6L, 2L squared, okay, 12 minus 6L, minus 6L, 4L squared, okay. Okay. And so, of course, those parts where the element stiffness matrices are overlapping, you just simply add those together. So, you guys can do that. In fact, it's going to be identical to the previous example. Okay. All right. And then finally, we have the entries for element C. And so element C is unique because it's a spring. So remember, a spring doesn't make any contributions to the rotation. And so this is going to be just D3Y, D4Y. And so all the rows and columns associated with that. Okay. So first we have the D3Y, D3Y location. So that's going to be this one right here. Okay. We have D3Y, D4Y. So it's going to be this location here. Same with this one here. Okay. And then we have the D4Y, D4Y location, which is that one down there. Okay. And of course, I made the matrix a little bit too small. Let me go ahead and. Okay. Now, when you're adding this entry here, the thing that we're used to is that we're used to just putting in directly the entries of that element stiffness matrix. Okay. Now, you have to be careful with this though, because we're combining different element types. And so, we're combining together springs and beams. Okay. Remember that kind of the implication here, or kind of the assumption is that we're multiplying this entire matrix by EI over L cubed. Okay. And so we have to factor that in when we're adding in our spring contributions, okay? Because our spring contributions here should just be a plus K, minus K, minus K, plus K, okay? That's what they should be in a vacuum, right? And so if there were no pre-multipliers, that's what they should be. But we have to take into account the multiplication of the factor out in front and cancel that when we add in our K times here, okay? So what we're adding in here is not K. Actually, let me zoom in just so you can see, okay? We need to multiply by K multiplied by the inverse of our factor out in front, okay? And so instead of K, we're going to multiply by K, or we're going to add K plus, or excuse me, K multiplied by L cubed divided by EI, okay? Minus K times L cubed divided by EI. Minus K multiplied by L cubed divided by EI plus K times L cubed divided by EI. And let me rewrite that minus 6L cubed. Okay. Okay. So the reason we're multiplying that K by that L cubed over EI, we're basically undoing our factor out in front here, which is like EI over L cubed. Okay, so we're multiplying that by the inverse, which is L cubed over EI. Okay. All right, any questions on this? Let me go ahead and zoom out so you can see the whole matrix again. Okay, all right, so that's all we got time for today. So it's 6:45. And so when we come back on Thursday, we'll pick up this example. We'll go ahead and apply the boundary conditions. And so we'll see how that's done. And then we'll move on to the last topic in direct stiffness, which is distributed loading. Okay. All right, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys on Thursday. Thanks, guys. Hey, what's up? Oh, sorry, I need to change that problem. Let me go back and.
Okay.
Yeah.
Because I was confused, I looked at the answer.
Yeah, so I basically combined this somewhere. I've shortened this section to off, just so we have more time for this. So it used to be there was some other stuff, but yeah, let me go and revise the whole.
Okay, so skip for now.
Yeah, skip, yeah, I'll send an announcement.
And the midterm is when?
It's gonna be,
It's on Thursday.
yeah, maybe Thursday, the last Thursday before Thanksgiving. So I think that's the 21st.
Yeah. Because in the syllabus it was this Thursday.
Oh, no, it's not this Thursday.
Okay.
It's gonna be, yeah, I can't open the calendar right now.
Yeah, I think
Yeah, we're
21st is a first.
Yeah.
Okay,
Yeah, we're a little behind schedule. Yeah, it's not this Thursday.
good to know.
Yeah.
Because I was prepared for Thursday.
That would be something to have
Yeah.
forward to after the.
Yeah, that's why I was confused.
Yeah,
But,
it'll be,
okay.
2 weeks from this.
Okay.
Yeah.
Exam, like, you have to calculate or-
Yes.
Okay.
Yeah.
calculate.
Yeah, so it'll be very similar to the problem.
Okay. Do we have to know MATLAB for the?
No. So the way the exam is gonna be, we're gonna have you set up the matrices. And then that's it. So basically write out the elements, get this matrices, assemble, apply the boundary conditions, and then that's.
Do we also have to like memorize theory that we have?
Yes. So for the exam, I have everyone write a cheat sheet, so that one sheet of paper front and back, and you can write whatever you want.
Okay. Perfect. I think that one makes sense. Oh, and so who's the exam?
It'll be 2 weeks from this Thursday. Yeah.
Okay.
I know, yeah, the syllabus at this, but we're kind of behind schedule a little bit. So,
Okay.
yeah.
Who's?
Yeah, sorry for confusing you guys.
Okay,
Yeah.
all right, good. Thank you.
Yeah. See you guys.